Today we will discuss simulation of simple harmonic motion. So we start with the spring mass system. So a spring attached to a mass, and the mass is displaced to position x naught. So the reference here is the equilibrium position, x equals 0. So we know that the solution of this motion is given by the function in harmonic terms. A cosine omega t plus B sine omega t, where omega is the square root of the spring constant divided by the mass. So the net force acting on the system is equal to negative kx x hat. So depending on the initial conditions, we can evaluate A and B. So to simulate this, we need to create a sphere for the mass and a spring for the restoring force, or for the attached spring. So for the inputs, first we put the system and we only need the spring constant as the input. K, let's say, is equal to 10. Spring constant. And maybe the initial position x naught. So we use the vector form. R naught is equal to x, y, and z. So we put a value for the x component, 1, 0, 0. And then the initial velocity. So let's make it initially at rest. So 0, 0, 0. Now we can make the object create the object. So we just add the attributes in the sphere for r position and velocity, initial velocity. So the position is r naught and the velocity v is v naught. So we also include the dimension attribute, say radius is equal to 0.5, color dot yellow. So just to check if we have created indeed a sphere. Now we create the spring. Spring 1. So for a spring, there's a specific object, helix. So the position of the helix will be the position of one end of the spring. And then the other end or the length of the spring will be given by the axis, and the direction will be of the same direction as the motion. So we need to include the length of the spring, L. Let's say L is equal to 5 times the length of, or 5 times the displacement, the initial displacement, so that we are sure that the spring length is always larger or longer than the displacement. So magnitude of R naught times the unit vector. So the unit vector should be in the direction of x, 1, 0, 0. Okay. So the helix will have position at negative L, and the axis will be equal to the length of the spring plus the displacement, the initial displacement of the mass. Now, since we already defined the initial displacement of the ball as R naught, you can put here ball 1 dot pos. Call mo na lang yun nasa taas. And then radius, we should have the same radius as the mass, 0.5. So here is the spring mass system. Now we are ready to simulate the motion. So make sure, class, that you put the unit vector in L. Okay. So if you change the initial position, let's say negative 1, then you have a compressed spring. Okay. So it is different when you define the length in the direction of the displacement, R0. So if you run this, if you follow the direction of the displacement, since the displacement here is negative, mag-iiba yung orientation ng spring. So if you make this positive, iba na yung orientation niya. So to maintain the orientation of the spring in the positive x direction, you need to specify x hat, vector 1, 0, 0. So if you make it negative, you will get the same spring orientation. Mako-compress lang siya pag negative. Now we can simulate the motion. So for the simulation, you need initial time, 0, and the time step, we fix it at 0.01. Then we can adjust them accordingly. Then we create while loop. So let's say time is less than 10 seconds. Then we fix the rate, 1 over dt. So inside the while loop, we will enumerate all the update equations. First is the force. So the force F is negative kx. So negative k. So since we are in vector form, multiply this with the ball's position. Ball 1 dot pos. Next, since we already know what is the net force, the update equation using second law. So let's try the form dp dt. So if you write the update equation, delta P is equal to F delta T, or P new is equal to P old plus F delta T. So that's the update equation for the momentum. So it has the same role as the update equation for the velocity. So first, we define the momentum. Dito na lang. So the momentum of ball 1 dot P is equal to ball 1 dot mass. Okay, so we need to add that attribute. Mass is equal to 1. And the velocity, ball 1 dot v. So the update equation for the momentum is ball 1 dot p is equal to ball 1 dot p f delta t, or plus equals f times delta t. And then for the position update equation, delta r is equal to delta v over delta t, or v dt. But delta v is momentum delta p divided by mass, or p divided by mass times delta t. We should have delta t at the numerator. V delta t. So the update equation is R new is equal to R old plus P over M delta t. Ball 1 dot pos plus equals ball 1 dot P divided by ball 1 dot mass times delta t. And for the time step, time is equal to plus equals dt. So that's for the ball's motion. Now you need to attach the helix. So before the time update, spring 1 that position should be equal to the position of the ball plus the length of the ball, or length of the spring, L plus ball 1 dot pos. So I think we need to adjust the location. Spring 1 dot pos. So this should be axis, not uh, it should be axis, not the position. So we change this to axis. So the orientation of the oscillation can be changed once you change the initial position. So if you change this to y, let's say 1, and you also change the length, so this will be in the y axis. So pag binago mo yung sign, negative, you have a compressed spring. Or you can have a spring on top, so you make it negative, and so on. So you can also have this value in z, say -1, and then run. So z is out of the page. So we go back to the original given condition along x 0, 0. And then we have 1. Now we want to map the function. So make a graph for x versus t, or r versus t, and r dot versus t. So graph, let's say this is the time axis, and y, this is the position in meters. So if we plot position versus time, you can use G curve, color, graph is graph 1. I-assign na natin because we might need another graph for the velocity and time. So we plot position versus time. So time and ball 1 dot pause. So you just plot one component at a time. So here we have the x component. So the function, as you can see, is a cosine function because it starts at its maximum point. So if we impose the condition, the initial condition from the solution, we have x naught, or x naught at time t equals 0 is equal to 1 is equal to a cosine of 0 plus b sine 0. So that means that a equals 1. So for the velocity, v at t equals 0 is 0. So we will have, so if you take the derivative of x, you will have a omega negative sine omega t plus b omega cosine omega t. Since t is equal to 0, this one is sine 0, which is 0, and cosine 0 is 1. So b is equal to 0. And using the first condition, a is equal to 1. So meaning the position function is 1 times cosine omega t, which is in fact we see in the plot. So if you want to verify Vt, so since b is 0, that means that x dot of t is negative a omega sine omega t. So it is a sine function. So if we plot the velocity, so we have another, you need to create another graph. Graph 2. Then y title is velocity in meters per second. So we create another graph or plot. Now this is v versus time. And then we put it in graph 2. So we change the height para maliit to 50 and width to 250. And title is position versus time. Then we copy for the next graph. And here we have velocity versus time. So this is the position. So we forgot to call v versus time. So take note, the function is negative a omega sine t. So ball 1 that v times x, and then run. So you can see that the initial velocity is 0. Now it should not be 0. Okay, so we need to define the velocity. So ball 1 that v is equal to ball 1 that p divided by ball 1 that mass. So you can see that the function is indeed a negative sign. So to verify the value for the frequency omega, this is square root of k over m. So k is 10 and m is 1. So you take the square root of 10 over 1. So square root of 10. So what we can do is to make this perfect square. K equals 9. So 9 divided by 1, and then take the square root. So the value is 3, since a is equal to 1. So as you change a is the value of the displacement, initial displacement. So if you make this, let's say 5, then the amplitude increases to 5, and then the velocity becomes 3 times 5, the maximum amplitude. So that's the method of simulating simple harmonic motion using the spring mass system.